Hello again and welcome. Today we're going to be looking at this AN8008. I ordered this meter, boy, I think it's been almost 3 weeks ago. At the same time I had ordered this Kasuntest ZT102. This is also known as the AN8002. I had previously tested this meter. I've also been working on a few other things. A friend of mine gave me this Fluke 189. This meter was used quite a bit in automotive repair. The lens over the screen was in pretty bad condition. So I purchased this stuff here. This is called Plastics, and this is made by Meguiar's. And what I'm going to do is show you a picture of before and after what this lens looked like. And it's incredible what this did for this. I also bought some of this Belkin True Clear Transparency, and so this actually has that film over the meter right now. So if you've got a scratched up lens, boy, I mean, this is the hot ticket. I just got this from a local AutoZone store. It's normally used to polish out your headlights. After I purchased this UT181A, I realized how soft this lens was, and unfortunately I put quite a few scratches into it. I know a few of you had commented how bad it was starting to look. So I've gone ahead and rubbed this out, and I also made a lens cover for it as well. You can see I've basically taken out all the scratches with this. Turned out very nice. I had also purchased these Fluke 97 scope meters, and these were also used in automotive, and the lenses on them were both pretty bad as well. So for this I actually wet sanded out the lens. It still has a couple of blemishes right here where it looks like somebody dropped a sharp object or something on there, so I didn't sand those out. I ended up using some 1000 grit and then some 1500 grit paper to finish it off, and then I rubbed it out with that Plastics. And again, it turned out really well. You can see basically no scratches left. And this had some pretty deep ones down in here. That's why I had to resort to the sandpaper before I buffed it out. So yeah, if you've got some really bad lenses, there are some ways to recover them. So this is the original AN8002 that I had tested. So one of the things that somebody had asked is, if the fuse were to blow, would it actually arc across the fuse contacts? I had actually ran that test essentially, and you can see that's exactly what's happened here. Assuming this shows up with the camera, let me just pull the fuse out. You can see the damage right in this area here. It's actually arced right across that fuse. You can also see the damage to the fuse right along the edge here. So yeah, it actually arced right over this. But again, these fuses are only marked 250 volts. If you looked at Dave's recent video where he was using an insulation tester to look at the AN8008 and a couple other meters, it was actually arcing across these two contacts. Of course, you can see with the meter that I actually tested, those contacts aren't even in play anymore. Those were completely vaporized, along with this trace heading up in this direction here. So one of the problems with this meter, of course, they've got the clamp up on this side of the meter. There's a PTC sitting here, and then your two diodes are here. These are your two high voltage, if you want to call them that, resistors. These are 5 meg apiece. These go up to the IC here. These go down to this common pad along here and then back right to the input jack. One of the nice things with the meter, at least they route to this side of the fuse. So if the fuse were actually blown, at least your volt ohm mode still works with this meter. You can see I've got my ESD gun out, and I've just got it attached right across the two current inputs of the meter. And what I'm going to do is turn up the voltage in this right there. You can see it's starting to break down. So you can see once the fuse here were to open, basically all that voltage would be felt right up in this area here is where it's going to break down. We could try this on the other lead. Unfortunately, basically the whole front end of this thing has been vaporized, so I doubt we're going to see any kind of breakdown anymore. That's 6 kV right there, and the meter's able to handle that just fine. But again, basically there's no traces that actually route to this connector anymore. Everything has been pretty much vaporized. You can just see that trace there is no more. So another thing somebody had asked is if these fuses were sand filled. I'm not sure. I've never had one apart. I would have thought maybe they were just ceramic for, oops, that kind of voltage. Yep, So there you have it. Nothing in them at all. These are just a plain ceramic bodied fuse. That was the 10 amp one. Let's have a look at the 600 milliamp one. Yep, same thing. See, no fill at all. So yeah, these are not safety fuses. And again, I wouldn't have expected these really to be filled, just with the body size being so small. You know, I already know that it's going to arc right across the two fuse contacts, even without a fuse. Basically what I'm going to do is clip to the one side of this fuse holder, and what I'm going to do is start increasing the DC voltage. Let's see if we can get it to arc. Oh, yep, right there. So that's at about 3,500 volts. You can hear it sizzling. Looks like it's arcing across the bottom of it. And this is about 3,000 volts right now that the generator's putting out. So yeah, definitely, as soon as the fuse were to open, it's definitely going to arc right across it with any kind of a transient. So one of the problems I had with this 8002 when I tested it last time is I was connecting up this transient generator, and this generator can output a full rectified AC signal. So that's at 220 volts and 60 hertz for us. And essentially, you would put the meter into the AC volt mode, and we'll enable the voltage. And you can see it's only reading 1.201 volts AC. The DC is correct, 235, and it looks to be a range problem. This meter again does not have a manual range, so I have no way to actually force it into the next higher up range. You can see if I run it with the little Fluke 101, see it's about 110 volts AC, and then the DC again is about 235 or so. Switch it back, you got your 110. So you can see if I kind of force this meter by disconnecting and reconnecting it, so it's 35 volts. There you go, 113. But now if I change it back to DC, so there's your 235. Now when I go back to AC, see 1.2 again. Let's have a look at the 8008 and see if it has the same problem. So there's our 235. And 115, that's what it should be. Go back to DC, that's correct. And back to AC, that's correct. Let's just try removing it and reconnecting. So you can see this meter has no problems with this at all. You can also try reversing the polarity. See, again, no problems at all. Let's go back to DC. See, negative 235. And then back to AC. No problems at all. So this meter, in this regards, does just fine, where this 8002 definitely has an issue with it. I also saw the same problem again with the 860B. It does the same thing that this little 8002 does. And again, we've seen other issues where the meters don't auto range correctly. So that problem is not all that unusual, that you can kind of creep up on it. But I think these are the only two meters, this 8002 and that 860B, that actually had a problem where they couldn't handle this rectified AC signal coming off the generator. So that's pretty unusual. It's also fairly common. I mean, you know, that you would work on a switch mode power supply, the first thing you're going to do is rectify the signal coming in, and you know, you go look at that with your meter, and you know, it's probably not going to read correctly if you've got one of these meters. So yeah, just keep that in mind if you're buying one, that these do have a quirk like that. So one of the things that really impressed me about this 8002, the frequency measurement on this could read up well into the 100 megahertz. I think it topped out at like 200 megahertz or something I had it up to. I believe that this meter may have been capable of reading the highest frequency out of all the ones that I've looked at. So let's just have a look at this 8002 and see how well it does. So again, I've just got this connected to my RF generator. We'll set it to hertz, and you can see we're already starting out at 17.1 megahertz. Let's just go ahead and we'll take this on up a little bit. Again, the other one I think conked out somewhere around 200 megahertz. Let's just take it on up a little higher. Oh, right there. So this is with a 20 dB signal, or roughly 3 volts. Let's just try this with the 8008. We'll see if it can handle the same. Oh, that's interesting. It does not like the RF. Look at this. It won't power up. Error. I guarantee you that's because that RF generator is attached. Alright, same frequency right there. And we can see it's not able to read it. Let's just adjust it down a little bit. Oh, still pretty good. Right there it rolls over. Yep. About 160 it looks like. But again, it's kind of funny. If I turn it on now, does it freak out? See, now it's coming up just fine. Let me take the frequency back up. So this is 200 megahertz. Check that out. The meter will not even power up with that applied. That's a 3 volt signal, 200 megahertz. Look at this. This meter will not power up with that. It's not even random anymore. At 200 megahertz, it just flat out will not power up. What's interesting too is it works the backlight from time to time. Check that out. I'll just disconnect the input. There you have it. Again, 3 volts coming off of this thing. That's it. 20 dB. Takes a little bit to get down there. You see it just slowly drifts down to 0. Not the fastest meter. So this is with a 0.5 ohm resistor. Again, this is a 1% part. Looks like 0.51. This is a 1 ohm 1%. And you can see it's just slowly drifting downward. Let's compare that against the 8002. So again, this will be with a short. You can see how much faster this is. This is a 0.5 ohm resistor. Of course, you know, we don't have that extra digit with this. And this is with a 1 ohm. And here's a 50 ohm. So let's just try the rest of them. So this will be 100 ohms. And this is again a 0.01% device. This is with a 1K ohm. This is a 0.1%. This is a 10K ohm. This is a 100K ohm. This is 0.1%. You can see it just takes it a long time to settle out. This is with a 1 meg. This is with a 10 meg. Really. So sure enough, it shows 9.999 mega ohm for that upper range. That's the top end of it. I mean, this is right at 10 meg. Right there. Huh. Let's have a look at the 8002. I thought for sure this could read this without any problem. There you have it. 10 meg. This is with a 40 mega ohm resistor. This is a 2% part that's on here. And let's just try her with 100 meg. Can't go up that high, but 40 meg. So if you're needing something to go above 10 meg, again, this 8002 definitely outperforming the 8008. Let's check the diode mode. So this will be a short. Here's a single, 2 and 3 diodes. No trouble with any of that. This will be capacitance mode. So let's try the 150 picofarads. Looks pretty good. This will be a 1 nanofarad. It's a 0.1 microfarad. This with 1 microfarad. And 10 microfarads. That's with 100 microfarad. Again, it's not very fast. So let's just try the frequency. This should be 30 hertz. So there's a problem with it right there. So this meter requires it go through the zero cross. So again, this is AC coupled, so you can see it's reading 60 hertz. And again, this is with a DC bias, so it's actually switching from 0 to 5 volts. And so again, it doesn't run through the zero crossing. You can see the meter can't read this. Let's just try that with the 8002. Of course, it can't read frequency in the voltage input. So here's your AC coupled, and this is with the DC bias, so that doesn't have any trouble with it. So let's try this meter with the hertz input. So it works there, so let's try it here. This should be 30 hertz, that's fine. 15 hertz, that's fine. 120, that's fine. So again, this meter doesn't support that mode, but if you're in the voltage input, it's definitely going to require the zero crossing in order for it to read the frequency. You can see right now we're putting out roughly 4.4 milliamps. All these meters are in series, and you can see the two are reading basically the same value. Let's turn this up a little bit. So here we're at roughly 87 milliamps. See, my power supply is drifting around a little bit, but again, two meters basically reading the same value. So this is with roughly 90 microamps being applied. You can see the 8008 can't read the microamp ranges. That's one of the benefits of this meter. Another question people were asking about was if this meter would survive the ESD testing. So one of the things I was wondering is just how close this circuit board comes to matching this one. So let's just have a look at this. Looks like the location of these two high voltage resistors are in the same proximity, but look at the beeper. It's been moved over here. Used to be over here. This area looks roughly the same. Again, you can see the PTCs located up here. Down here is your clamp. So the problem again with this meter is that the switch contacts of this would still have to survive the full hit right on the input jacks, and pretty much guaranteed that's not going to happen. Looks like the trace coming off of here may be a little bit thicker now. But you can see they have not changed this area here. So this is another location that I would expect this to break down. Again, if we put high voltage with the fuse open, even if it didn't break down across these contacts, I'm not so sure that this location here isn't even closer. Looks like the diode here is in the same location. You can see what was marked as the range switch, and this is SW3. SW3 is marked up here now, so they've moved the location of that. But yeah, they're similar, but quite a bit different, really. I mean, as far as hitting this with an ESD pulse, you know, I couldn't say that this meter would actually survive like this one without actually running it. The circuit boards are different enough that, you know, I would be just guessing. That's why we run the test. Let's have a look at the back side of it. Again, even the switch contacts are laid out a little differently. You can see it's marked ZT109 version 0.4. Looks like the switch contacts look the same between the two. This next test we'll be looking at the 3 dB point for the AN8008. So both meters are in series. You can see I'm applying a 60 Hz waveform. This is a sine output. And you can see we are at 1 volt. This looks about the limit of it right here, so about 3.04 kilohertz. Let's just try this the other way. So it's quite interesting. You can see the 3 dB point for both meters is very similar. To the left here I have our high voltage power supply, and we're just going to make sure that this thing can handle the rated 1000 volts. One thing I noticed with this power supply, so you can see we're putting out about 21 volts. As I turn this off, see how it's starting to load this down? So that's the most I can get out, and that's just because of the loading of this. So again, if we switch this over, see we're about 45 volts. Turn it off and you can see we're down to 7.6. So let's have a look at the 8002. You can see this meter works the same way. And I also noticed that with the 860B, basically when you turn these meters off, they basically ground the input. And again, I'm not sure why they do that, if that's for some kind of transient protection, maybe for static. But you can see it's quite a load. If we look at the little Fluke 101, of course that doesn't have a problem with this. And likewise with the 189, you can see we turn it off and supply just stays up just fine. It's really just these low end meters that I'm seeing that problem with. Something again just be aware of when you turn them off, that they do go to a fairly low impedance. Alright, let's go ahead and take it up. And again, the 8008 should be good for about 1000 volts. And that is the limit of our power supply right there. You can see it's quite accurate. Alright, so again, both meters are attached to our high voltage power supply. And currently you can see we're supplying a 100 Hertz waveform. Notice how when I switch this over to Hertz, it actually draws down the power supply. So looking at the Fluke, you can see the DC voltage in the lower center. It's basically 0 volts DC and 543 volts AC. And the AN8008 is showing about 250 millivolts. If I select the AC mode, you can see it's 540 volts versus 543. So it looks like, again, the meter is fairly accurate. Let's go ahead and we'll add some DC bias to this. It's pretty good. So we have about 440 volts of DC bias, and this is positive. You can see it's not really affecting the output of the meter. Let's try going negative with it. It's about negative 540 volts of bias, and again, the AN8008 is not having any trouble with that at all. See, it looks like, at least from reading 1000 volts, the meter doesn't have any troubles with that. So for this next test, we'll be switching the meter through all of its modes except for the current with a full rectified 220 volt AC waveform. You can see with it in the voltage mode, we're outputting roughly 235. That's pretty normal. And in the AC mode, there's our 116 So there's the millivolt range, resistance, and frequency. And again, I won't look at the milliamp ranges. Alright, let me functional test the meter. Okay, it looks like our little 8008 passes that test just fine. So a few of you may have noticed that I'd taken down all my videos for the 121GW. The reason I did that is Dave was posting about how he was concerned that people would be confused by those videos. So even though that I was basically stating that they were pre-production, you know, that there would be some concern that people would still assume that that's the way the production meters would behave. But one of the things that came out of that was the last video that I had made was, again, I was temperature testing the meter. I got a little bit of grief from Dave out of running those tests because, you know, of course I'm running them with a millivolt input, and he's running, I think, at like 4 volts or something, and he's up on the volt range where I'm down in the millivolt looking at the muck. And again, typically the meters that I've looked at, I don't think I've seen one drift more than 2 millivolts, even with all the test leads in there. And I'm not saying that we're not having some kind of thermocouple effects, you know, with my cabling and such. Most of that's going to get canceled out when I run it anyway, you know. So it's kind of interesting because David posted that they actually changed some stuff for the temperature again. So this is after they made the change for the actual reference they were using. They made another tweak, and apparently that was for the millivolt range. So I asked him how they actually ran that test over temperature, because that's basically what I'm doing. I'm interested in looking at the millivolts. And he never responded, so I don't know what actually went on with that. So there are 2 people that had asked about comparing these 2 meters over temperature, and what we're going to do is run that test. So those 2 people don't really care about me running these outside of the manufacturer's temperature range. They'd just as soon see us run it the way that I've ran all the other meters. So what I'm going to do again is apply a 1 millivolt source to both of these, and we'll run them, you know, from -20 up to 60 degrees C, and let's just see how these 2 compare. Alright, so you can see we're back in the environmental chamber. We've got the 8002 on the left and the 8008 on the right. You can see I have a 1 millivolt source applied right now. And again, our Fluke standard is just sitting outside the chamber. So I think what we're going to do is just run this to 0 degrees for starts. Come back in about a half an hour and we'll see how these things are settled out. Alright, I've just changed our set point to -10 degrees C. Alright, I've just changed the temperature. We're now going to -20. Alright, for fun, I just thermal shocked both meters. You can see the humidity build up in the chamber. So I crack the door open, take a second for the chamber to recover. Okay, it's starting to come in a little bit here. So you can see I changed our reference over to 1 volt. We'll give them a couple of minutes to restabilize, and then we'll collect the data off of them. Okay, so I've had both meters at -20 with 1 volt applied for some time now. You can see the last digit of the 8008 still moves around a little bit. The 8002, on the other hand, is quite stable, and it's only 1 count, it appears to be. Right, we've been up at 60 degrees for a while now. See, we're about 103 and 991 maybe. See, the 8002 still moves around about 3 counts. Right, you can see I've changed both meters over to 1 volt. So a day has passed since I ran the temperature testing. Basically what I wanted to do is make sure that there's no moisture left in either of these meters. So looking at the data for the ANENG8008, when I ran it at -20 it was reading 1.048 millivolts. And at 60 degrees C it read 0.991 millivolts. So that gives us a difference of 57 microvolts. That's actually pretty decent. That's better than the Bryman BM869S. That measured like 89 microvolts. But my X-Tech EX540, that was about 570. The AN8002 measured 0.94 millivolts at minus 20 and 1.03 millivolts at 60, so that gives us a difference of 90 microvolts. So a little bit more drift with this guy, not much. Another thing that I did is I went back and I looked at the susceptibility of this to RF. Basically I wanted to know if there were any other sweet spots. So I manually swept the generator up to about 500 megahertz when I was manually turning this on and off. I didn't see any other location where it had a problem with it. It looks like the band that's really the issue is about 199 megahertz to about 207. So just be aware of that. My concern, the next test that we're going to run is going to be the CSD, and it's fairly high frequency. This thing puts out about a 4,000 volt peak at 15 amps, and it does that in under a nanosecond. So because of the high frequency and this thing being susceptible to high frequency, it'll be interesting to see if this thing will actually survive this test. Again, I can feel this in my fingers. It definitely is more severe than what that little grill starter is. So what we're going to do is apply 5 transients in each mode of the meter, and then we'll do that in both polarities. Then we'll go back and functional test it. Alright, that's it. Let me go ahead and functional test it. Alright, so it looks like the 8008 passes the ESD test just fine. Alright, so next we're going to be running our mini surge test. And again, we're going to be starting at 1000 volts. This will be a 50 microsecond full width half height and a 2 ohm source impedance. A couple of things I'd like to mention. I had ran the 8002 prior to running this 8008. This meter was damaged at 3000 volts with a 50 microsecond full width half height. And compare that with this Fluke 101. This meter survived all the way up to 13,000 volts with a 100 microsecond full width half height. So that's 2 times the normal full width half height that I typically run the meters at. I've seen a couple of comments recently about this testing. Again, I'm kind of surprised that people still bring this up. The comment was basically that I was directly discharging capacitors into these meters. Again, that's not at all what these transient generators do. So if you're really interested in what goes on inside of these transient generators, I'd suggest that you actually procure a copy of the IEC standard. In there they talk about the coupling network and how that all kind of works. So this waveform is actually with the meter disconnected, and so that decay is actually created from the output network inside the transient generator. So what ends up happening normally is when I'm running these tests is the meter is not actually what dissipates the energy. It's actually dissipated inside the generator, and that's all done through that coupling network. So unless the meter actually goes to a low impedance state, really no energy is dissipated inside this. So again, this will be 5 transients at 1000 volts, and again we'll do that with each mode of the meter. I'm not going to test this function generator output or any of the current inputs. Alright, that's it. We'll go ahead and functional test the meter. Alright, so the meter passes functional test just fine. I've gone ahead and reset our generator for 1.5 kV. And again, this will be a 50 microsecond full width half height with a 2 ohm source impedance. So you kind of wonder, when I run it at 1000 volts, typically I run DC into the meters at about 1000 volts as well. What's the difference? Well, if they have any kind of a capacitor in there to block the AC and it's not well protected, what can end up happening is that high frequency edge, because the slew rate of these transients is about 1.2 or something microseconds, that high speed edge can actually blow through that capacitor and damage some of the circuitry. So just because it passes 1000 volts DC doesn't mean it'll survive that actual AC transient. I've seen that before on some of the meters where they've actually failed that test. Alright, that's it. We'll go ahead and functional test the meter. Alright, so our meter passed that test just fine. So I've reprogrammed our generator for 2000 volts. Again, 5 cycles each. Okay, that's it. Alright, so the meter survived that test just fine. Next we'll be running 2.5 kV. Again, this will be a 50 microsecond full width half height with a 2 ohm source impedance. 5 transients, positive and negative, each mode of the meter. Oh. That might be the end of her. Let's see if it'll power back up. Nope. I'm afraid that's it. So that was 2,500 volts with a 50 microsecond full width half height. So again, this guy failed at 3 kV. In the ballpark of one another. I guess I'm not too surprised with the circuit board and the design the way it is being very similar between these two meters. I doubt there's anything we can do to repair this. We'll go ahead and take it apart. So I've taken a look at the meter, and essentially what's happened is we've shorted the power supply pins of this. If I hook this up to a power supply, it's definitely the chip up here that's been damaged. This thing will begin to get hot. So yeah, there's nothing I can do to repair the meter. It's unfortunate, but quite expected. Again, the very first meter of this, same problem. So what I'm going to do is just hook this back up to our transient generator. We're going to put it back in the millivolt range. This is where it was damaged at. And let's just see if we can tell where this is breaking down at. Alright, here we go. Well, just blew the casing right off of the main IC. So just for comparison, when Dave was showing the insulation tester being used to check the meters, again a very crude setup, I think those insulation testers are somewhere sub 2 milliamps. We are applying basically a 2,500 volt transient, less than what he's got, but we're limited to the 2 ohm source impedance, so we're putting out about 1200 amps initially when this thing hits. And this is at about 20 joules max that we can deliver with this particular transient generator. So a fair amount more energy than what he's able to get out of that insulation tester, and that's why you see the damage that you do. Let's just put this thing in jig. We'll run it off of our half cycle line simulator. Okay, so I have the high-speed camera out. We're just going to do a fire with the main transient generator without the half cycle one enabled. And let's just make sure that the camera is working. Alright, we are set to go. Everything is armed. Alright, let's go ahead and we'll take this thing apart, see what it looks like on the inside. First sign of damage right here. See this trace? It's discolored just slightly. Also see this trace up here. Alright, so notice this trace here. This is basically gone. You can see it's actually collapsed, this one switch contact. See on the far side, that got so hot it's actually melted into the plastic. Looks like most of the traces in this area are just basically gone. Some pretty rough condition. Let's take a little alcohol. Let's just have a look, see what we really got here. There you go. Give you a little bit better view of what's happened. You notice when that copper gets onto the circuit board, it doesn't just clean off. It's almost like it plates it. You can't rub that off. I've gone in before and tried to repair meters like this, and I'll take some wet sandpaper and grind that out of there a little bit. Anyway, it's just like before. So this trace here is totally gone. The pads up here where Dave was showing them arc between the two, you can see those pads are basically gone. There's quite a few pads up in this area. Those are etched away as well. Yep. So somebody had talked about what would it take to basically add a MOV to this, and could you protect it? I would want to put everything up in this corner here, so there's just not a lot of room. I could remove the fuse and stick essentially 2 PTCs up in this area with a couple of MOVs. I could do it with probably just 2 MOVs, you know, and then limit the voltage to something less than the 1000 volts that the meter's rated for. Basically remove this PTC up here, short that, and leave this clamp where it's at. You could probably get this thing to survive. I just don't know. There's just not a lot of room up here. Problem is the meters, you know, you can see they already have other issues. It's hardly worth the effort to put into it. It's not like the UT61. That actually is a fairly decent meter, you know, for what it is, for the price. These meters just seem to have a lot of issues. So I don't think I'm going to do anything more with it. Well, I think that's going to be it for this video. Hope you enjoyed it. Sorry it took so long, but it took a while to get my hands on one of these meters for some reason. It's been on order for quite a while. Looks like we have quite a few new followers since I've posted my last video. Glad to have you on board. If you're interested in seeing these meters tested to failure, like this one here, this is definitely the channel to come watch. So until the next meter, we have a look at this 8002. Later.